I'm Victoria, and I'm a scientist from Picsart, and today we will be discussing photosynthesis and the representation of the synthetic. So, first of all, what is the direct problem? How do we solve the direct problem? What problems are imposed by the direct problem? And then we can get to the first problem. The direct problem is rendering. During the process of the rendering, we have a 2D model or we have a 3D object scene. And rendering is the process of generating a single image given a scene file. So the scene file can contain like just a 2D model, just like in the cases of SVG, it has only the 2D model. The scene file can contain the 3D model. For example, if we're trying to render a scene in 3D Maya or an OBJ scene and so forth, it can contain the 3D model. The 3D model has its texture, it has shading, it has shadows, lights. There's a camera that looks upon and tries to capture everything. So that's the process of rendering. Here we have two examples. The example above, only rasterization is depicted, and the example below, everything is much more complex because we have complex light algorithms and how the light interacts with the medium. So how do we render? For rendering, we need to solve the rendering equation. AKA, we need to compute the illumination that comes from a certain object. The object that is given at a point X can have, so basically the light that comes out of it is the sum of the light that it emits itself, and the sum of the light that it reflects, the light that comes upon it and then it reflects. So the rendering equation depicts just that. LE is the emitted light. Emitted light is really important because if we're trying to like render the sun, or if we're trying to render a light bulb, it is a combination of the light that emits itself and the light that is projected upon it. And here we have an integral. This integral is actually really important because later on we'll see that it's absolutely essential for everything to be differentiable. And it takes the FR function. The FR function is dPrdF, meaning it's a function that states how the light interacts with the medium. So the light can be scattered, just like in Muradyan, scattering, the light can be reflected, and so on and so on. LE is the emitted light, and everything needs to be normalized, so you need to take the normal component of the direction it's heading out. And how do we solve this rendering equation? It can be done in multiple ways. So we can solve everything by rasterization. Rasterization is the most simple thing that we can do. We can just get the objects and we can just project it upon the scene. Ray casting is a bit more complex. We have a light source, so we direct a ray upon the object. The ray gets scattered, something happens. It interacts with the medium in some sort of way, and then there's a camera that captures that ray that's going. So we do this for individual rays, and that's how we get ray casting. And finally, we have ray tracing. Ray tracing is an alternate, not an alternate, it's a GPU accelerated version of ray casting. And we use Monte Carlo techniques, meaning we have to track each and every single individual like flight. These are not it actually, there are some lots of approximations, such as spherical harmonics, just like in the case of games. You try to use spherical harmonics to solve the rendering equation because everything can be done much faster. It's a polynomial, it's basically a polynomial that can be mapped upon ray tracing. And ray tracing is used nowadays. You can see like NVIDIA that nowadays has GPUs that can use ray tracing, like RTX GPUs. So now rays describes like we have 3D points and then we project it upon the 2D plane and we end up getting a 2D image. But what if we try to preserve the 3D-ness, just like we can draw a 3D image on the paper, correct? We try to get that effect using computer vision. For that specific question, we need volume rendering. In the case of volume rendering, we try to give a correct representation of the 3D points upon the 2D scene. So for volume rendering, we need to fix. First off, we need to define the camera position relative to the volume. Just like in this case, this is a skeleton of the mouse. Volume rendering is used in MRIs, it's used in games, and so on. You guys might have seen this multiple times. So in this case, it's a skeleton of the mouse, and the camera is put directly in front of it. Also, we need to define something such as voxel. So we have pixels in the RGB space, aka we have the x and y coordinates, and for every x and y coordinate, we have an RGB like RGB toplet or RGB A photos. In the case of voxel, it's the equivalent of a pixel in the 3D space. So we have an x, y, z coordinates, and for that we try to give it some sort of color. Now, how the camera can be positioned? It can be positioned in multiple ways. First of all, it can be positioned in a fixed way. Just like if you have done the rendering, if you have written fragment shaders using OpenJL, you might have seen it just puts the camera upon the scene, and then you can create 3D optical illusions. That's the fixed camera positioning. Then it can track the object, meaning it can follow the object from behind, and the user cannot interact with it. So it just follows the object, nothing can be moved. And finally, we have interactive, which is most commonly used in the games. So the user can move everything within a certain degrees of freedom. It's actually 5 degrees of freedom, and so from now on, when I say dimension, you need to imagine degrees of freedom. So if something can move within 5 dimensions, it means we can change the x, y, z positions, we can change the theta of it, meaning how much it's skewed, and we can change the phi of it, meaning just like vertically how much it is skewed. And finally, we have the inverse problem. So this is view synthesis. In the first case, we had the object, and we had every single information about the object we ever needed. It was created by a human, so we knew the texture, we knew the maps, bump maps, normal maps, how it interacted with the medium, and so on. However, in the case of reverse problem, we just have the rendered images, we have the rendered scenes, and we need to somehow recreate the object back. So if we formulate this problem differently, we need to predict a missing depth axis. However, we will learn in the future that depth axis approximation isn't really necessary. We can just formulate it using different components. So what is radiance field? Well, first of all, what is radiance? Let's say we have a given point in time and the light passes through it with a certain direction. So the amount of light that passes through it, we call it radiance. And the radiance field is an approximation of the electromagnetic field. However, we only take in components that us humans can preserve. Like, that's understandable for humans. If you guys have a physics background, you might know that the electromagnetic field has polarization, it has wavelengths, it can be transformed, and so on. However, we don't need that much information because humans themselves do not perceive all that information. We just need the simplest thing from the electromagnetic field, which is the color. And that's what radiant field is. So for every single point, for every single light direction, it gives you the RGB triplet. And then we finally have the rendering equation. So how can we bring all of this to the rendering equation? Well, luckily we have an integral operation, and we can define this as a linear operator with infinite dimensionalities. Just like how we do it with functions like x, x squared, and so on, it's an infinite dimensionality linear field. So that's the same thing with the rendering equation. And it can actually converge, so it can actually have the form of a fixed point equation. And its convergence, you can basically say this by you can basically give a really mathematical approximation to it and the mathematical proof to it why it should converge. And using the Banach theorem, we can just say that it needs to interact with something. And that's actually really intuitive. Let's say you have a light and you have an empty room. If there's nothing to interact with, the light isn't going to be seen at all. So for you to be able to see the light, it needs some sort of interaction with the object. And that's what the convergence of the radiance field states. So how can we incorporate all of this into deep learning? So here we have neural radiance field. Given a set of input images, the volumetric representation of scene is regressed as a continuous vector function from the specified coordinates. And like as you can see in this video example, we have the X, Y, Z RGB. So we take a video or we take multiple photos of the scene. And then in some way we try to get the 3D representation of it. So in this case we get the 3D representation of it. We move within certain degrees of freedom, and then we can use this as a model. And why is neural radiance field a lot better than any other approaches? And why is this considered the state of the art? Because here we have a continuous function. Like previously, people used to just optimize the volumetric representation, which actually took a lot of space. You couldn't make it that compact, and you ended up having a discretization artifact. But in this case, since it needs to regress the continuous function, everything can be done much more smoothly. How can we actually train this network? So we have 3D random, so we just generate random points. Then we try to remarch. Remarch meaning we like emit a ray and then see what happens, how it interacts with the medium and how the camera captures it. So we define this point, we try to remarch, and then the camera captures it, and we end up getting a specific scene. And this scene scene is somehow corresponds to the images. So in this case, we have like multiple images of the given scene. We just need to make sure we get an object from it. And how can we actually train this? Well, remember when I said that the rendering equation is a differentiable function. That's what guarantees us that it can be trained, because we end up setting it taking the images. Sorry. We end up taking the images and then we try to calculate the L2 losses of different images of different scenes, and that's how we train the whole network. However, this approach was quite revolutionary, but it had a couple of disadvantages. For example, it depended on the photometric variation. So we take photos at different points in time. We take photos with different cameras and so on. Everything is just going to end up becoming parsed and not really beautiful, and like you cannot get correct approximations of everything because everything depends on the color. The color will be blurred, smudged, and so forth. The second problem is the problem with transient objects. So what are transient objects? They're objects that are not part of the static scene. Just like people, anything that moves and anything that is not a part of the scene, it can be assumed to be transient objects. And the transient objects will end up getting really blurred. And the next paper actually approaches these two problems. So we have nerf in the wild. And what it does is, first of all, why it's in the wild? Because it uses just like random data sets of random scenes. And it depends on the image itself. So like previously we took every image, we viewed every image in a single way. Now we have to view every image separately and we have to get some sort of embeddings out of the images so they can be modified upon the static scene. So as you can see here, now it has dependency on the type of images. So we made two modifications to the classic nerf. First of all, we have the appearance embedding layers added to the classic MLP. And what this does is basically tries to get rid of all the redundant information we're never going to need, such as color and so forth. So we just try to get the semantic approximation of the object, and we end up getting the static output for the static scene. And then for the transient objects, we end up adding the transient embedding layer, which again gives us the prediction of RGB color and gives us the prediction of density. Density is basically how much light is passing through it. But it also gives us an uncertainty field, and uncertainty field is really important because it tries to tell us how many what pixels are specifically transient pixels and what pixels are not transient pixels. So the transient field, basically the uncertainty field, is incorporated into its loss function as a form of segmentation loss, and it ends up just neglecting all the transient objects, and so we can reconstruct the static scene. And here you can see the picture below. It's the transient scene, and the picture above is the color corresponding representation, radiance field representation. However, nerf in the wild also has a couple of disadvantages. First of all, the most prominent disadvantage is you need to overfeed upon a single scene. Meaning if you try to run it upon some data, the test data needs to be really similar to tree data, so the embeddings can be approximated, which is not really useful, especially in the case of production, because you cannot restrict the user to a specific scene. You need to make sure it works in multiple different cases. So it still has problems generalizing normal scenes. And it's really, the data itself is really hard to collect, and any sort of inconsistencies can become problems. So camera calibration is really important, and parts of the image that are not seen usually, they will end up getting blurred and so on, as you guys can see in the picture above. And finally, we have dynamic resynthesis. So before this, we had different images of the scene, and we tried to approximate the model. In this case, we have a monocular video, and we try to not only approximate the scene, but we also try to move it in the time, and then move within the scene with certain degrees of freedom. So how we try to solve it? We try to train two nerves independently. One of them is a static nerve, which is in a time invariant. So for each and every single scene, it's time invariant, and the other one is a time varying dynamic nerve. And the results are joined in an unsupervised manner. However, the dynamic nerve cannot really converge because there are multiple representations for the same scene. So for that, we need multiple regularization losses to achieve more physically valid solutions. In the case of the static nerve, everything is quite simple. It's just the nerve that's used in nerve in the wild. We have the 3D position and viewing direction. We put it through the MLP. We end up getting the density, embeddings, and the color. So, and then we ignore all of the transient pixels. So that's how the static nerve works. And in the case of the dynamic nerve, something else is predicted. You guys might be familiar with optical flow or scene flow. It basically tries to see which pixels of the scene are moving and in which direction they are moving. This is actually really important because using the optical flow we can track, and using the optical flow we can make sure that the scene from t minus 1 to t, the scene from t to t plus 1 actually corresponds in some sort of way. Because let's say you have a hand, if you move the scene, the hand might just end up getting broken or separated in multiple ways. And that is a major concern because it again can be a valid solution, but not a valid solution in the human form. And then we have a couple of regularizations. So first of all, it's the motion matching loss. As I said, there is the optical flow. So we try to make sure everything is within a certain range, just to track pixels like you behave the same way. Then there's motion regularization. As it can be seen in this image, the certain C from P can correspond to multiple scenes in P plus 1. And since we not only move through the 5 dimensions x, y, z, theta, phi, we also move through the time dimension. We need to make sure we have the best probable matching. And for that, we add a motion regularization loss, which is basically an L2 loss that provides a smoothness. Then we have sparsity regularization, which what it basically does is it keeps alike objects it makes sure that alike objects tend to act like in a alike way. Like we have the dinosaur here, it makes sure the dinosaur doesn't become some creature. Then we have depth order loss. So for this specific paper, they trained a state-of-the-art depth network, and then they try to incorporate its data upon our training. Why? Because closer pixels tend to move faster, and farther away pixels tend to move slower. So you need to have some sort of information about what the depth is. So depth gives you more information about what objects can be transient, what objects can be static, and so on. Then we have 3D temporal consistency loss. This is what I talked about when you move the scene. You need to make sure that no objects crash and the objects stay at home. And rigidity regularization loss. This is a way to provide that rigid objects do not end up crashing. However, this again has a couple of disadvantages. First of all, non-rigid deformations are not handled very well. Just like as you can see in the case of the humans, everything is blurred. And not only that, if you have like a spring or a silky, it cannot really be modeled in a correct way because it has too complex motions to be modeled. And then dynamic nerve heavily relies on the optical flow. So if the optical flow itself is not predicted correctly, then it will end up becoming blurry and inaccurate estimates will be made. And the most prominent flow, and why we don't see this in production yet, is because this takes immense amount of resources, human resources and computational resources alike. So you need to overfeed upon a single scene. And to overfeed upon a single scene, you need to input an immense amount of human resource. You need to calculate the camera calibration, camera positions, and so on. And the computational time of this takes around 20 minutes to get a correct approximation. So that's not really production ready. However, it is research ready, and the future is actually bright. So over the last 2 years, over 50 papers have been published on this topic, and here you can see they have been published in different titles, ranging from depth estimation to neural rendering, 3D reconstruction. Even I remember there was super resolution image generation. Even they all try to use the neural gradient fields in a way, meaning that there is a lot room for improvement, and all of the top universities and research labs are working on it. So advancements have already been made, such as speeding up the process. There is the technology known as pre-baking. So we know what the model is going to be. We generate the embedding layers beforehand, and then we try to approximate, fit a single scene to a single model. That speeds up everything a lot, and that shows a lot of promise. Then separating dynamic and static components are done quite well. Like a lot of progress has been made in that direction, and we can see in the figures that I presented. And synthesis from a single video is also growing. Just like if we have more than one camera, then everything is a lot better because we will have some information on the depth. However, if we have a single camera, then depth estimation is again not viable. So we somehow need to get the depth estimation to make sure that everything is better. And as I mentioned, this topic is actively researched by multiple labs, such as our parent lab, Facebook AI, Google Research, the University of Oregon, Berkeley, and so on. And as a side note, I remember 2 years ago when, again, you guys might know papers. So like 2 years ago, they didn't show any promise. Everything just crashed, and I kept thinking, it's going to be the time that this actually reduces to normal result. And nowadays we have Stallion ADA, which overperforms. Honestly, I am surprised by it. So given how fast this industry rises, I am more than sure that we will see all of this in production and we will use it in our daily lives. So, any questions?
I have a question. So you said that you were getting the 2D representation from 3D using the depth axis. Can you explain the intuition behind it?
The intuition behind this is actually, we humans do that a lot. Just like, have you ever tried to draw a cube on a piece of paper?
I understand it, but more of a mathematical way of thinking.
Mathematical, like how you render it?
Yes.
Or
the process or some intuition behind the mathematical
yeah, basically, there isn't such thing as intuition. There is the case of need. So we had games, and in the case of the games, you couldn't really have individual images drawn in every single case. It would be a lot more useful for you to have a single scene, and then just like project it, render it upon certain images. So for that, we came up with the terms of rendering, and for that, we ended up trying to solve, as I stated here, we tried to solve this rendering equation. So this is actually something we see a lot in optics, and whenever we had this problem, we noticed that it's quite similar with the problem we had in optics. So that's how we came to the thought of we can represent the 3D models upon the 2D space. It's more of like a on need basis. There isn't like such mathematical intuition. We just saw a problem. We saw that there is a solution in physics. So we tried to combine those together.
I lost you very, very early on. So can you go to the slide with Muradyan's? The very first one where you... Yeah. So what were those theta and phi parameters again?
Okay, so you have the horizontal axis. Theta is the angle it makes with the horizontal axis. Let me check. Okay, so you have this horizontal axis. You try to rotate it to a degree. This will be the theta parameter, and phi will be this.
Okay. So and by XYZ you represent this RGB?
Yes, at the end it interacts with the object, it ends up getting a certain color, and the camera ends up registering it as the color that it interacted with that one. So that's the intuition behind it.
Okay, and how do you solve it again?
By the rendering equation. I can actually, if anybody has any questions, I can actually send you the full explanation of how the radiance fields work. It's actually quite complex, so if I have to cover it, it would take more than an hour. So you guys can just find me on LinkedIn and I can just send you really in depth how the radiance field can be generalized as a linear operator.
Please don't say.
As you wish.
All right, any last questions, please?
Which feature beside the Picsart application uses what you described?
We are not using this yet. Actually, we did this as a project during the hackathon time, and it showed quite a amount of progress, so we started researching it independently. But we hope that we have certain amount of achievements in it so we can push it to production.